Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
So just a quick introduction to FANUC Robotics. We started out as a project at General Motors Research, and it was the NC painter. That stands for numerically controlled painter, which was a robot arm that was to be used to paint cars. About 1982, General Motors decided that it wasn't their core business to be in the robotics business, so they joined forces with FANUC of Japan, which has expertise in servo control and motor development. And FANUC of Japan also does many CNC machine tools, which are computerized numerical control machine tools that are fully automatic to carve metal. About 1992, GM ran into cash problems during a recession, sold its half to FANUC. And so at that point, we became fully owned by FANUC Limited of Japan. And we also changed our name from GM FANUC Robotics to FANUC Robotics at that time. So far, to date, we've installed 150,000 robots in industries around the world. That makes us #1 in the industrial robot business right now. Also, we're about 50% market share in North America. So we've been rising a couple points each year, and now we're about 1 in 2 of every robot sold in North America. And we have 200 current variations of robots that we use for different applications. And so there's a few of these posters back there if you haven't seen them. This is the base models of our robots, and there's variations on each of these that are available. And the reason you would use a different robot for different applications is if it has a different payload, or it has different speed requirement, if it has different accuracy requirements, you match the robot to the application. So here's a quick outline of our talk today. We'll start out with how an industrial robot works, recent advances in industrial robot technology, and then we'll move on to things that aren't robots but start out close to robots and then move farther and farther away, beginning with telepresence devices, moving on to haptics, and we'll look at some assist devices there, and then finally with some prosthetics that are very close to robotic technology. So what is a robot? Here's the definition from the dictionary. It's a lot of words, and at the end, you can see that the word robot derives from a Czech word, robota, which was used by a man named Karel Čapek as a title for his play, Rossum's Universal Robots. This is where the name robot comes from. And it means drudgery, and it's the kind of work that a person wouldn't want to do, so you'd have a machine to do it. I've got my own definition. I can break it down to 3 words, what my definition is. Programmable automatic mechanism. By programmable, what I mean is the robot is adaptable to different tasks, that you're able to program it and it does different things according to the program. Second, it's automatic, that fundamentally it doesn't need human intervention to work, that once you start the robot, it operates on its own. And finally, it's a mechanism, that this isn't just a box that sits and thinks in the corner. This is a machine that operates on real things in the real world. It actually moves and manipulates objects. So when we look at some of these things that aren't robots, keep this definition in mind about why it's not a robot. It might be not a robot because it's not programmable. It might be not a robot because it's dependent on a human to generate consistent input for it to drive it. So just keep that in mind. So on the topic, how a robot works, there's 2 basic parts of the robot. That's the body and the brain. For industrial robot, the body is generally a mechanical arm. And so we'll take a look at how the mechanical arm is put together. And then the brain part is how do we make the mechanical arm move? And so we'll take a look at the different parts of that as well. The fundamental unit of a mechanical arm is a servo-controlled axis. And when you take a look at this picture, what you see is a black motor waving what's basically a yellow stick. So as the stick moves up and down, the motor is controlling the angle of it. You can see that there's a coordinate frame at the base, at the motor, and at the top. So what the motor is basically doing is manipulating this coordinate frame at the end of the stick. in terms of generating the movement of the robot, what we're trying to do is move it to consistent coordinate positions. And the servo controller here takes this angle command, and that's the command that we want the motor to move to. And so it'll generate a current, which is a direct analog for torque to the motor, to move the stick. And then it's watching this red thing, which is an encoder. This is an angle measurement, which is accurate, very, very accurate. It's like 64 bits per revolution, and there may be multiple revolutions through a gear train to move one revolution of the link. So you can see that the servo controller is able to match the position of the robot link to the command, and the command is ultimately coming from the brain. So if you take a few of these and chain them together, we get a kinematic chain. And again, starting from a base coordinate frame, you can jump from here to here to here to here. And it's a simple matter of trigonometry to figure out where this end position is relative to this first one. And so if you have, little feedback here, if you have a knowledge of what the angles are of each of these joints, you're able to derive what this position is in space. And fundamentally, that's what the robot is doing, is manipulating that position in space. Also, each joint of the robot, each motor provides 1 degree of freedom. And we're going to look in a second, we're going to see that a robot needs 6 degrees of freedom to fully manipulate an object in position and orientation in space. And that's because, as you know, we have 3 dimensions in space. If you're a robot, your x direction is straight up. Your x direction is straight ahead, z is straight up, and y is to your left. So we have those 3 dimensions in position that we can move to. Then there's 3 dimensions in orientation. There's 1 rotation around each of these axes that you can do. And you can demonstrate these with your neck. For example, yaw is turning your chin to the left and right like this. Pitch is forward and back. And roll is rolling your ears towards your shoulders like this. So you have 3 degrees of freedom in your head in orientation. So as we go ahead here, here's a little animation of the robot. It's going to exercise each of the joints. So you can see how each joint moves around. The first 3 links are generally used to move to a position, and the last 3 are used to move to an orientation. So the gross motor function of the robot comes in the first 3 joints, and then the final 3 is the close orientation control. What you can see here, I just wanted to point out on this one, is that you can see that the 3 motors that control the wrist are right here. The wrist is this area. There's 3 axes in there, but the motors are back here. The reason they're back there is because this motor, which controls the elbow joint of the robot, would have to lift them if they were sitting out here. And by lifting those motors, it adds extra weight, which reduces your payload, or it requires a bigger motor to do. So by moving the motors to strategic positions, it increases the payload of the robot. Also, when you see this end position of this end effector, you can see that we need 6 degrees of freedom. That's 6 joints to do each of the 6 degrees of position and orientation freedom. So that's the basics of how the robot arm is constructed and how it works. Now we'll take a look at the robot motion as it's controlled inside the robot brain. So we'll take a look at each of these blocks from the program through planning, interpolation, inverse kinematics, and the servo command is ultimately the angle commands that go to the motors to tell the motors what positions to move to. The motion program is simply a set of instructions that say, move from here to here at this speed using this trajectory. And so just as a simple example here, move from point A to point B in a straight line. So the user of the robot, this is what they would teach. They would teach this program, and the robot would then follow the program as it operates. Planning is the first step of digestion of the program. The robot is doing things that don't need to be computed in real time. It's variables that you can compute and then save to use the results for later. So you don't have to compute them every step along the way. So that helps you to save time during interpolation. Interpolation takes place many times a second, and anything you can remove from interpolation helps to save processor time for other tasks. So in our example here, this move from A to B will take 750 millimeters and need 372 steps along the way. Moving on to interpolation. This generates for each step of the robot, a real-time position in space for the robot to move to, which is a position and an orientation coordinate. So at this example, the 187th step is at this coordinates. So you can see that in order to have smoother robot motion, basically what we're doing is sending these coordinates to the motors. You want to send smaller steps more often. So ideally, you want to take small steps every interpolation period and send those to the motor. If you take too big steps, the motors start to become jerky, and as a result, you have to take smaller steps. So if you can't process fast enough, it makes the robot move slower overall because of the processor speed limitations. And so we're going to take a quick look here at inverse kinematics. Now, if you remember, forward kinematics is to transform from the robot joint angles to the orientation and position in space at the end of the robot arm. Now, inverse kinematics is the reverse problem. If there's a position in space you want to move to, how do you find what the joint angle should be to reach there? So it turns out that this is a tricky thing to do, and it's very tricky computationally, and this is where a lot of the processor time of the robot takes place. One thing is that there's more than one solution. If we run this little video again, you'll see that the robot is arriving at these same positions using different joint angles to get there. So you can imagine if you hold your arm out and your fist is a position in space, you're able to rotate your elbows to different angles. So there's actually, in the human body, an infinity of potential solutions to this problem. What this is showing is what happens if you interpolate in joint space instead of Cartesian space. So what we mean by interpolating in joint space is that your joints are moving from here to here, and so each joint individually follows its own path to that space. And if you can picture yourself drawing a straight line, how your arm has to move, all your joints are changing speed simultaneously and very carefully keeping in sync with each other. So this second line from the top, this is actually a straight line. The top line is if you follow those same two coordinates, but use a joint interpolation. It introduces a bend to the path. So if you want to draw straight lines, if you're cutting something, for example, and you use a joint interpolation to save processor time, you're going to get bendy lines. And because of the multiple solutions, if there's a difference in turn numbers, that is, the robot has extra solutions, you can go, say, half a turn around the wrist and then flip the wrist the other way and have the same solution on the other side, which is what these bottom two ones are. You can get some really wacky moves if you're looking at what the end effector is actually doing. So this inverse kinematics is extremely important to do, but it's also processor intensive. And here's an example of what the solution would look like. This is just 4 pages out of my early robotics book. What you see here is the partial solution for the first 2 joints of the robot. And you can see some of the complex geometries that are involved and some of the nasty equations. It involves a lot of strange inverse trig functions, which are not only hard for a person to do, they're computationally intensive for the computer. So a lot of 15, 20 years ago, a lot of what the computer was thinking about when it was deciding how to move the robot was how to control a position, and there wasn't a lot of processor time left over for interesting things. Now, more recently, processors have gotten faster, so this has taken less time, which allows us, first of all, to take more steps along that line every second, which allows the robots to move faster. Let's see if, I'll just continue on this a little bit more. It also allows potential to control more than one robot with the same processor. It allows you to do more interesting things. And so we're about to take a look at some of the more interesting things in a second here. So here's just the review of what the robot motion signal flow looks like. And when we take a look at some of the non-robots later in the presentation, we'll refer back to this, and you'll see how it's different than the way the robot works. So I just mentioned that the faster CPUs allow you to solve the inverse kinematics problem faster, which gives you more interpolations per second, smoother motion. It gives you faster accelerations for that same reason. That because you have smoother motion, you can accelerate faster without exciting the vibrational modes of the robot. And what you don't want is a jiggly robot with a laser, for example, on the end of it, cutting jaggy lines. Okay? And because you have faster accelerations, you wind up with better cycle time, which means you can manufacture more parts per hour. Also, because we're able to control the robot better, we're able to make the robots lighter. We're able to deal with more flexible robots. The links don't have to be as stiff. So we remove metal from them, and they start to get a little more floppy, but the software is able to compensate for that. Now, that helps you in several ways. First of all, the motors don't have to be as big because the robot's not as heavy. It costs less to manufacture the robot because it has less metal in it. And also the payloads can go up because now you're not lifting as much of the weight of the arm. You're able to put more of that power of the motor towards the payload, not towards the arm itself. And because we've got more processor time available now, we're able to do some more advanced control methods. And so I just talking about compensating for link bending and vibration of the arm. We can also detect unexpected collisions that we're able to predict the dynamics necessary to move the robot arm. And so if we see variations in the torques going out to the motors, we can tell that something has gone wrong and stop the robot. We're also able to do coordinated motion. So a robot could have a program taught relative to a coordinate frame that's on another robot that itself is moving. And so we're going to take a look at that in one of our videos coming up. We're also able to do some machine vision. Now, robots historically have been kind of stupid machines. They're blind, they don't have a sense of touch. So everything has to be precisely located for them. We call that positive location. And unfortunately, in a plant, it's a very expensive thing to install because everything has to be in exactly the right spot for the robot to pick it up and use it. Because if anything's in the wrong spot, the robot can't adapt to it. So what vision allows us to do is to identify parts that aren't where we expect them to be, identify variations in parts, and even check for quality issues. Also, there's force control. Now, if you can imagine backing up your car, say up to a telephone pole and just touching it, and then the kind of force that's generated backing up another inch is enormous. The robot has the same problem. When it touches things, it can generate enormous forces because the robot is position controlled. What that can do is damage things pretty easily, and it makes assembly of tight things and things that are in the wrong locations hard to do because everything has to be exactly known in advance. So what force control does is it gives a sense of touch to the robot. And so the robot is able to feel its way through things the way a person would. It's able to feel that this direction is not working, but this direction is working better. And so we'll see a little bit of force control later on. So first of all, collision detection. This is working by predicting the dynamics of the robot arm and watching for disturbances in torque. So what you're going to see this robot do, it's going to hit this first plate, and it's going to blow right through it because it's not paying attention. And this is what would happen in an industrial setting if maybe you weren't paying attention or something was in the wrong place, the robot would just smash it. The reason you don't want to do that is because this robot might have a $20,000 or $30,000 tool attached to the end of it, and you don't want to explain to your boss why you smashed this up. So this second plate, when it hits this one, it's going to detect a torque disturbance and stop the robot instantly. It'll drop servo power and turn the brakes on, and you'll actually see the robot shake because it stops so suddenly that it induced a vibration in it. But that second plate will be undamaged, so we'll just take a quick look at this video. Is it coming? There we go. So the first one smashed. So there you go. So that's an important thing to have for a customer, particularly if you're working with expensive tooling. Now this next one is an example of coordinated motion. This object on the left is a Ferris wheel parts holder. Okay? So this has an axis of rotation in the center, so this entire thing can spin around. This big black thing in the middle is a door. What these robots are going to do is arc welding, and the arcs are dangerous to look at, so you usually do it in a closed environment so people don't look at them accidentally and burn their eyes. Now, each side of this is holding a part, and in this case it looks like maybe a table leg, like a stainless steel table leg for food handling. And there are motors here and here. So this thing on the left is a funky robot of its own. It doesn't look like a robot arm, but it really is controlled by the robots. And you'll see this start to move, and these two robots here, there's one here and one here, are each going to do arc welding on this. And they're going to do it in such a way that all three of them are coordinated together. The two robots on the right are not running the same program, and so you'll see them all move independently but together in a way that allows them to weld the parts. So let's take a look at this one. So you can see as that part moves, the robots are adapting to the movement of the part and doing the weld. Of course, this isn't something you could normally look at with your bare eyes. So you can also see why robota is the Czech word for drudgery, because you can imagine welding a couple hundred of these a day and how much you'd like your job doing that. Now here's some two-dimensional machine vision. By two-dimensional, what it means is it's looking at things in the plane, and it's able to identify their position and orientation in the plane. So there's a light up at the top here. Somewhere up here there's a camera looking down. So it's going to watch these parts go by, and as they go by in the conveyor belt, it's going to note their position and orientation. The conveyor belt has an encoder attached to it, so we're able to know the exact position of the conveyor belt as it moves along. And the robot is going to be able to pick up 3 of these at a time using the end effector, pick them up in the correct orientation, and put them down in this tray, organized. So I think these parts are Pop-Tarts or something of that kind. Okay, so two-dimensional machine vision, and you can see how the parts are disorganized, and the robot's able to deal with that. Now we'll take a look at three-dimensional machine vision. So in an auto plant, for example, it's very expensive to send parts in trays that are organized. It's much cheaper to send them in a big bin like this where they're all dumped together, and you just pick them out as you need them. But of course, this is a very difficult thing for a robot to do. So what's in this robot cell is at the top, looking down, there's a two-dimensional camera that is looking into these. These are piston rods inside a big basket here. It's going to identify potential candidates to pick up. And then the robot has, right about here on this end effector, a laser range sensor that's able to identify the orientation of the piston rod. So once it's identified candidates, it'll take a look at it, an individual one, and figure out what angle it's at, so it'll try to be able to pick it up. And so what you'll see is the robot picking up piston rods out of this disorganized mess and putting them down in an organized way over here as if it was feeding them to another machine. Okay, so that's an impressive demonstration too. I think that was at a trade show or something. Okay, so what we're about to take a look at here is robots building robots. This is a force control of a transmission for a robot. And it's going to assemble bearings and gears into the transmission using force control. Now these have very tight tolerances. Our robots are built to last for about 60,000 hours before their first maintenance. And if you think about that, if you drove your car for 24 hours a day, Monday through Friday, after 10 years, that would be about 60,000 hours. And at that point, you'd need to change the oil. Okay? So that's the kind of precision that we're trying to do with the robots. And also, as far as accuracy goes, when the robot moves its arm around, typically, it knows its position to within 1/10 of a millimeter in space. And in order to do that, everything has to fit very tightly in the transmission. And so what you're going to see here is assembly of the bearing into the transmission, which is done by feel. Then you'll see several gears inserted onto pins with I don't know if it's micrometer or mil tolerances, but it's very, very tight. And then the final gear has to go in and mate with the first two. And it'll do all of this under force control. So here we go. It doesn't look like it's doing much, but it's actually very carefully managing the force on that. We don't want to bend it, and we don't want to break any parts as we put them in. So it's feeling for that, that pin. So you see it took a while for that one to find the right direction. So there you go, it's managed to mate all the teeth on those gears. So just watching the video is not impressive, but knowing what it's doing is pretty impressive. Okay, so at this point, well, actually, here's a different kind of evolution. This is an evolution of attitude, going from about 20, 25 years ago to today. That back then, people thought robots are stealing our jobs, you know, robots are evil. And now, it's not robots stealing jobs anymore, it's, you know, they're going overseas. It's being offshored. So now robots are saving jobs from offshoring. And so there's this marketing thing, Save Your Factory, SaveYourFactory.com, that is able to demonstrate how robotic technology and automation is able to bring down the cost of manufacturing in the United States to the point that it's cost competitive or better with other countries, even countries with very low wages. So this has been kind of a boon for us. This is something that it's our business too. Like if there's no factories in the United States, that's who we're selling the robots to. So it's to our advantage to sell the robots in the United States. And the companies in the United States, it's to their advantage to keep the business in the United States. So this has been a very successful promotion. It's not just Fanuc Robotics, it's many robotics and automation companies. So now moving away from robots and starting to get into some things that aren't robots, I'd like to start with telepresence. And the key points about telepresence is, first of all, it doesn't have a predefined program anymore. It has a human operator driving the machine. It goes through a communications network and sends a trajectory. Some of these also have inverse kinematics, some don't. And then that becomes a servo command. But then there's a feedback loop as well, that they're sensing either video or some kind of force sensing that's fed back to the human operator. And what telepresence implies is a distant interaction. At a long range, you're able to manipulate things and interact with the environment. So we'll just take a look at a few examples of this. There we go.
Dr. Dennison is like many doctors, overextended. He can spend hours in surgery. He has patients at 2 different hospitals. So this is how he makes his morning rounds.
Good morning. Good morning, Dr. How was your first night after surgery?
As part of an experiment in California, Dr. Dennison works the controls of a robot called Ruby. He can steer it down a hospital corridor from his office computer across the room, even from home, using a camera and screen to have two-way conversations with patients such as Irving Down.
May I take a peek under your dress in there?
Yeah. The camera can zoom in to give the doctor a clear view.
Doesn't make you a better doctor. It makes me a more available doctor. And if that's better, great.
Okay. So if you've ever been in the hospital and your doctor couldn't see you because he was someplace else that day, so he sent maybe a colleague that didn't know you or a student that didn't know what they were doing, you know, wouldn't this be better for him to be able to interact with you directly even though he's not on site? So you can see it, even though this looks kind of hokey, it's got a lot of value to it. And it can also obviously be done pretty cheaply. So this is something I think we're going to see more of in the future. NASA's got a thing called Robonaut. And what this is telepresence for space, that when you send an astronaut outside of a controlled environment in his spacesuit, first of all, it's a very dangerous situation to the astronaut. It's a high radiation environment. And the astronaut's trying to operate inside a pressurized suit, which is, it makes it hard for him to work and he gets tired fast. So the idea is, you build a robot, and this one is It only goes down to the waist. He's just got like a bolt at the bottom of his waist here. So you're able to bolt it on, say, to the space station, or maybe onto the shuttle's robot arm, and wave it around to where it can reach. And then the astronaut has control of the robot arms and the head, and he's able to see what the robot sees through the head of the robot. So let's take a look at this.
Robonaut is a teleoperated robot, meaning that a human operator can control its movements from a distance. The teleoperator with a head-mounted display will control the head of the robot and can see what the robot sees.
Okay. So you can see that there's no force feedback to the astronaut. That's one thing that they're probably going to have to work on. That it's very important for him to hold his hands in the right positions, because you can tell it, as you're interacting with things, you're generating forces on them. And, you know, what if he sneezes or something? So it'd be his advantage to have more feedback in terms of force feedback. But you can see there's some potential here too. There's lots of places in space that are just too dangerous to send people into, and you can imagine places like that here on the surface of the Earth as well. At an extreme example, here's the Mars rover. This is like telepresence all the way to another planet. It is kind of telepresence, and it's kind of telerobotics, that the communication leg is so long going out to Mars that basically what we do on Earth is send a program, and at the end of the day, we see what the results are coming back. But in a way, it's telepresence as well, because we're manipulating the surface of another planet. So I don't have a video of this one. Now I'd like to start to get into haptics. And so there's two words here that are defined. One is haptic, which is things that have to do with the sense of touch. And so we're going to be taking a look at some machines that interact directly with people by either the people touching them or the robot touching people. We're also going to talk about proprioception. And what this is a sixth sense that allows you to know the position of your body in space without having to look at it. So you can imagine that athletes and dancers, for example, have a very strong sense of proprioception. And likewise, if you've ever seen a cop do a drunk test, he asks you to touch the tip of your nose with your finger, with your eyes closed. That's how you know how to do it. It's through proprioception. So we're going to take a look at three examples here. We're going to take a look at the intelligent assist device, and then exoskeletons and robotic surgery, and how these are all examples of these haptic sort of devices. So the intelligent assist device is very much like a robot arm. It's almost exactly like a robot arm, except the commands aren't coming from a program. They're coming from a human input. So the human takes a hold of it and applies force to it through a force sensor or some other sensor. And that force gets processed into a trajectory. And that trajectory is what the machine is going to follow, unless it doesn't want to. And that allows us to put in virtual walls, for example. It'll prevent you from crashing into things by accident or damaging fragile surfaces. And think of it as kind of like a horse, that you can tell the horse the direction to go, but unless the horse agrees, you know, it's not going to happen. And the reason you would use something like an intelligent assist device is that there are a lot of parts, you know, you see a lot of this in auto plants, but there's other places as well, that aren't easy for the operator to handle. They're too large or too clumsy or just flat out too heavy for the operator to deal with. And so what the intelligent, so he's able to operate the IED by grabbing onto it, pushing, pulling. It's kind of like driving almost like a shopping cart in 3 dimensions. Okay, so it's able to tip up and down and go up and down. And if you had a hover shopping cart, that's what it would do. So it uses the advantages of the robotic servo control. It knows its position in space, and it has the power of a servo control, along with the operator's intelligence, that the operator is able to steer out of trouble in places that the machine wouldn't expect it. And it allows a power assist to provide a gravity negation, so you can lift the part so the operator doesn't have any of the ergonomic stress on his body that would be caused by lifting heavy objects. Also, there's no inertia, that the machine is able to absorb the inertia so that the operator doesn't feel it. If you're, say, pushing a 300-pound shopping cart and needed to stop suddenly, you'd appreciate that. Also, I just mentioned virtual constraints, which it can prevent you from crashing into things by accident, or it can guide you through narrow places. And we'll see a little bit of that in the video here. But by the way, this was my baby. I did this. And so this is an awards video that displays the device, but unfortunately we don't manufacture this anymore at Fanuc Robotics because there's a huge engineering cost involved in installing this that automakers want things to be more and more idiot-proof to the point that you almost don't need the idiot anymore, and so I have the device. And so for us, we don't make this product anymore. There are other companies that do similar things, though. Oops, I'm sorry. Didn't mean to skip ahead there. Get my cursor up.
In today's manufacturing environment, large finished vehicle models such as instrument panels are brought together for final assembly. Although traditional lift devices can handle these large and cumbersome parts, they are problematic as they pose physical and technical fatigue upon the operator, create overall quality issues, and have single application capabilities, making almost 50% of them obsolete. A team from Ford's AMTD facility, along with Fanuc, a robotics supplier, found the solution to this manufacturing dilemma by designing and implementing the Intelligent Assist Device, or IAD. This cutting-edge technology not only can be used in multiple applications, but it also proactively addresses both ergonomic and quality issues. The first key element to the IAD's design is the human force sensor located on the handlebars. This unique sensor detects the force of the operator and enables him to have complete control over the speed and force of the device's movement, relieving both physical and mental fatigue. The second is the innovative feature of virtual walls. These walls are actually passive motion boundaries created by the IAD's programmable motion constraint software, which provides guidance for precision placement, protecting both the finish quality and physical integrity of the parts. In 2003, the IAD was implemented at the Michigan truck plant and has shown a 70% safety reduction in operator injuries and has created a total savings of $7.8 million to date.
Okay. So if you have a 2003 or later Navigator or Expedition, this machine put in your instrument panel. And some of the advantages of using this machine is that before we had put in the instrument panel unloaded, it didn't have things like airbags and the radio and all those things that add weight to it because the operator couldn't manage the weight anymore and it would wind up smashing into the doors or the B-pillar as it went through the door. So this device is able to put it in with all that stuff already installed, which means you're able to free up space on the line, which saves money for that car company. It's also able to do it without ever damaging the part. If you saw him going through, it has the door already on the car, and he's able to squeeze through the door. He's only got a ½ inch of clearance on each side of that thing going through. And the machine is able to guide him through there so that nothing ever gets scratched or bunged up. So now if you think about how this was mounted to the floor, it's on a big rail that ultimately comes down on legs to the floor. What if you didn't mount it to the floor? What if you mounted it to a person instead? Now we're starting to talk about exoskeletons. You can see how we're moving farther and farther away from robotics now, that this technology is evolving into something that's not robotics anymore. So what an exoskeleton is, just like the human assist device allows you to lift things that are too heavy for you, the exoskeleton strengthens your body directly. There's a couple reasons you would do this. One is to strengthen people that are weak. The other is to allow a person to lift a heavy load or carry it for a very long distance. And so what you see on the left here is the Japanese conception of what an exoskeleton should be. And on the right is the American conception. The Japanese idea is based on, both of these are based on where the research money is coming from. On the Japanese side, it's coming from a civilian organization. On the American side, it's coming from military. And the problem for the Japanese is that they've got an even bigger baby boom Social Security problem than we have in America. That as their baby boom generation begins to retire, there literally won't be enough people in the country to care for them all because their birth rate has been so much lower than ours. And so their idea is if we're able to strengthen elderly people, say, for instance, they're able to still walk up to their third floor walk-up apartment instead of going into a nursing home, that frees up a lot of resources in the country. And so this one on the left is really for mobility of elderly people. And you can imagine possibly using something like this for someone that, say, is paraplegic, has paralyzed legs, even in the future. So you could be able to avoid wheelchairs. On the right is the American version, and it's obviously a military or paramilitary sort of thing, something that a soldier would use or possibly some kind of rescue squad. The idea is that you carry a very heavy weight, say you have a couple 300 pounds in the backpack, and you're able to carry it for 15 miles, and you don't get tired. And that's what we would like to do. You can see from these that one drawback of these relative to the assist device we just looked at is that these have to be self-powered. They have to carry their own power supply. And like a robot, they have to carry their own weight. So whatever that power supply weighs is less payload that the machine is able to carry. So let's take a quick look at video. Here it is in action. This is the Berkeley exoskeleton. And I would guess from the sound of it that there's a gas-powered generator running in that backpack that he's carrying around. Now, you can see that the operator doesn't have real good balance yet. There's still probably some issues with the servo control and dealing with balance. But that's more of an engineering thing that can probably be worked out over time. But you can see that this is something that's definitely coming. That Japanese version was supposed to be released this coming fall at a cost of something like $13,000. It's affordable. But like I said, the power problem is an issue, particularly if you're carrying heavy weights. I mean, where do you get the energy from to do that? Okay, so the next thing we're going to take a look at is robotic surgery. And the robotic surgery we're about to look at doesn't really meet, my definition of a robot, which is the programmable automatic mechanism. It's neither programmable nor automatic. It's driven by a person and not by a program at all. Some of the advantages of robotic surgery we see up here, which is, first of all, the robot doesn't have to lean over the patient for hours at a time, so he doesn't get as tired, which is, if you think about it, if you're under the knife, you'd prefer your surgeon not to be tired. Also, what we're going to look at, you'll see the surgeon moving his hands in the controls. He's using his sense of proprioception to move the controls, so inside the patient, the robot is doing those same motions. But the surgeon's moving his hands maybe an inch or two, and the robot is moving maybe a millimeter or two. So there's a scaling down of the motion going into the machine. That scaling down itself reduces tremor. So as the surgeon gets older, his hands start to shake, it becomes less of an issue with robotic surgery. And also the machine itself can reject tremor, can reject input at those frequencies. So the tremor can be reduced directly that way. And so, my hope for this sort of machine is that it will give surgeons a longer professional life. They won't have to retire as early because of fatigue or tremor in their hands. And given what it costs to train a surgeon, that's a good thing for society in general. Also for the patient, it's less invasive. You have a much faster recovery with this than if you have customary open surgery. The disadvantages are the robot is still very expensive. And also, it's no better than the best surgeons. A highly qualified surgeon will have about the same end results as the robot. But, I kind of think of it this way. Maybe you don't need as highly qualified a surgeon to get the same results in the future with the machine. So we'll take a look at the machine here. This comes from the Minds of Medicine show. It's from Henry Ford Hospital, downtown Detroit. And they're using their machine for prostate surgery. Okay, so that's a very impressive machine. It's not what I would call a robot, but it is very much like an assist device for the surgeon. And you can see a couple really neat features of it are that it sort of defies a category for what exactly it is. It's in some ways telepresence, that the surgeon is operating as if he was inside your body, not from the outside of your body looking in, but actually inside looking at the pieces. It's also an assist device, and that, I talked about the reduction in the motion going in. But it's an impressive thing. So now we're going to move even farther away from robotics, and we're going to start to talk about prosthetics, which is the branch of medicine dedicated to artificial body parts. What we're going to take a look at here is a man that has he's a double amputee. Both his arms have been removed at the shoulder. And so if you can think about what your life would be like if you couldn't use your arms, how would you brush your teeth and cook food, and who would tie your shoes and stuff like that. Now, let's see here. Here's a couple examples, pop culture examples of what prosthetics are. The $6 Million Man had an arm and a leg and an eye replaced with prosthetic versions that were in some ways robotic, but they were controlled by his nervous system, and so they behaved as if they were part of his body. And lucky for him, they gave him superpowers too. On the bottom, you see Dr. Octopus, who doesn't have really human prosthetics, but he's got extra arms attached to him that he's able to control with his mind, that allows him to do more things. So we'll take a look here at the human signal flow. Remember what robot motion control looked like? Basically, all this stuff takes place inside your brain, even the inverse kinematics. That when you reach out to touch something, you're not really even thinking about what motion your individual joints need to do to get there. You just do it because this is like an automatic function of your brain. And so all that's left over for prosthetics is what we call a muscle command. It's the actual mechanical piece. If we can get the command from the brain to it, it would be able to function as if it was your actual body part. So what we're going to take a look at is this man who's a double amputee. His name is Jesse Sullivan. And there's a Dr. Todd Kuiken at the Rehabilitation Institute of Chicago that's been working with him to develop a robotic arm to replace one of his arms. Now, it's not like you might have seen in the Matrix or something like that, where you can jack directly into your nervous system to be able to do this. There is no probe that can talk directly to your nerves and be able to extract what you want the arm to do without damaging them over time. So instead, they've surgically taken the nerves that ran down his arm to the muscles in his arm, and they've grafted them onto an arm and a muscle in his chest. So into his pectoral muscle, these different nerves connect. So in his brain, when he moves his arm, the muscles in his chest twitch, and we're able to pick that up with a myoelectric pickup. So we can't connect the servo directly to the nervous system. So we connect the nervous system to extra muscle, and we pick up the muscle twitch, which is pretty coarse right now, but you're going to see that this is a pretty impressive video. And based on that muscle twitch, we're able to issue servo commands to the motors. Let's see here.
Later, researchers out of the Rehabilitation Institute of Chicago, headed up by Dr. Todd Kuiken, say they too have the technology to rebuild a person after the loss of an arm. He says his regenerated nerves working in conjunction with his new digital arms give him greater mobility over traditional prosthetic devices.
And he's using it for everything. He's painting a truck, he's working on his house, he's starting.
Dr. Kuiken says nerve transfers and lost upper limbs are only the first step.
We think we can apply it to many levels of education, not just shoulders or elbows, but for people who lost their hand, and perhaps even for lower prostheses.
Okay. So right here, you can see all these myoelectric pickups that are being used to drive the arm. And what's interesting about this, you may have seen other prosthetic devices that pick up when you twitch another muscle. So you have to kind of teach your brain how to move that muscle to move your arm. This from his brain's perspective, it's sending a command to his arm. He doesn't have to learn anything to make this thing operate. It's just, he moves his arm the same way you move your arm, and he doesn't have to think too carefully about it. And I think that's just a really, really impressive technology. You can see how the servo control on this is a little primitive right now. Obviously, all the parts of this are going to continue to improve over time, and it's going to become more and more natural looking. I mean, if you had a sleeve over that, you might not notice that it was a prosthetic arm. And it also, like it says, it gives him extra mobility and it allows him to do things he wasn't able to do before. I mean, gardening, how cool is that? So, that was the last thing I was going to talk about today. Here's just a wrap up. We started with how the industrial robot works and how industrial robots have evolved to have more and more capabilities, and then moved on to telepresence, haptics, and then finally this thing at the end is prosthetics. All that's left is the mechanism. The entire thing upstream from that is gone from what a normal robot is. So I guess that's all for today.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.